All right, let's talk about something we do every single second of our lives. Motion. Seems pretty simple, doesn't it? But, to really describe a journey perfectly, you need a special kind of language. So, let's dive in and learn how to speak it.
Okay, so imagine this. I tell you to walk 500 meters. Simple enough, right? But where do you go? You could walk forward, backward, left, right. You could walk in a big circle. That instruction is incomplete. It tells you how far, but it gives you zero clue about where. And that little problem? That's right at the heart of how we understand motion in physics.
So, to solve this puzzle, physics gives us this really precise language. It's a way to communicate not just the how much, but also the which way. And with this language, we can describe any journey with total clarity, whether it's just a walk to the shop or a planet orbiting the sun.
And the foundation of this whole language, it all boils down to two key concepts that we're going to break down right now: scalars and vectors. Seriously, if you get this difference, you've unlocked the key to everything else. And you know what? The difference is actually super simple. A scalar just gives you a magnitude. That's it, just a number. It tells you how much. But a vector gives you both the magnitude and a direction. It tells you how much and, crucially, which way. So let's zoom in on scalars for a second. A scalar quantity is all about its size, its magnitude, and nothing else. Think about it. 30 seconds, 5 kilograms, 10 miles. These are just numbers. They don't have a direction, right? You'd never ask, which way is that kilogram? They're just pure, simple amounts. And then we have vectors. A vector needs both pieces of the puzzle to make any sense. A force of 10 newtons, pushing down. A speed of 50 miles per hour, due north. See? If you leave out the direction, you're literally missing half the story. And just like that, our original problem of where to walk is solved. Okay, so let's put this into practice. We'll start with the most basic question you can ask about a journey. How far did you go? But as you're about to see, there are two very different ways to answer that, which brings us to the classic showdown: distance versus displacement. Think of it like this. Distance is the total, winding path you actually traveled. It's what the odometer in your car tracks, every single twist and turn. But displacement? That's the shortcut. It's the straight line as the crow flies from your starting point to your finish line. One tracks your entire journey, the other just tracks your change in position. So, for the official definition, distance is just the total path length you covered. Let's say you walk 3 meters east and then turn and walk 4 meters north. Your distance is easy peasy. 3 plus 4 is 7 meters. It's a scalar, just a number. That's it. But displacement? That's a whole different story. It's the distance you covered in a specific direction. In that exact same walk, your displacement isn't 7 meters. It's actually 5 meters in a northeasterly direction, the straight line from where you started to where you stopped. And here's the kicker. Displacement must have a direction. So how do we actually specify that direction? Well, we use something called bearings. This can be as simple as just saying north or south, or getting a bit more precise, like north 40 degrees east. Or, if you want to be really exact, you use a 3-digit angle measured clockwise from north, kind of like what pilots and sailors use. So we've figured out the difference between the path and the shortcut. Now let's talk about how fast we're traveling. This brings us to another pair of physics terms that get mixed up all the time: speed and velocity. And look, the pattern continues. Speed is our scalar buddy here. It just cares about how fast your distance is changing, no direction needed. Velocity, you guessed it, is the vector. It's your speed in a specific direction. The speedometer in your car, that tells you your speed. But the GPS telling you you're heading north at 60 miles per hour, that's your velocity. At its core, speed is just the rate of change of distance. You travel 100 meters, it takes you 10 seconds, your speed is 10 meters per second. That's it. Simple. It's a scalar. Velocity, on the other hand, is the rate of change of displacement. It tells us how quickly your position is changing and in what direction. And get this, you could be moving at a totally constant speed, but your velocity could be changing constantly. Just picture driving around a roundabout. Your speed might be steady, but because your direction is always changing, so is your velocity. All right, so we've got the lingo down, but how can we see the entire story of a journey all at once? For that, we need to pull out one of the most powerful tools in all of physics: motion graphs. I mean, a list of numbers and times is useful, sure, but a graph tells a story. It lets you see acceleration, constant speed, stops and starts, all in one quick glance. So how do we do that? Well, let's start with a distance time graph. On this kind of graph, the steepness of the line, what a mathematician would call the slope or the gradient, that tells you the object's speed. The steeper the line, the faster it's going. And if the line is flat, that means the object has stopped. It's basically a visual speedometer.
But the real powerhouse, the heavy hitter, the tool that unlocks the deepest secrets of a journey, that is the velocity time graph. This is where it all comes together.
And this is just brilliant. A velocity time graph gives you two crucial pieces of information for the price of one. First, the slope of the line doesn't tell you speed anymore. Now it tells you acceleration, which is the rate your velocity is changing. And second, the area underneath the line, that tells you the total distance the object traveled. It's incredible. Two huge insights from one simple chart. So think about what that means. We can take the most complicated journey you can imagine with speeding up, slowing down, constant speeds, and we can just break it down into simple shapes on a graph, like triangles and rectangles. By finding their slopes and their areas, we can analyze every single moment of that journey with amazing precision. So there you have it. You now have the tools. You get the difference between just a distance and a precise displacement, between raw speed and a directed velocity, and you know how to read the story of a journey written in the lines of a graph. So the next time you're in a car, on a bike, or even just walking down the street, take a look at the motion happening all around you. What story is it telling?